All right, geometry, here we go with the end of chapter 10, section 2. So earlier then, in the last video, we talked about two formulas for the area of a trapezoid and the area of a rhombus. The third one we have to do is area of a kite. And the good news for us is that the formula here for area of a kite is absolutely identical to the formula for area of a rhombus that we just talked about. It's 1/2 multiplied by the length of one diagonal multiplied by the length of the second diagonal. So it's the same formula here for area of a kite that we talked about earlier then for area of a rhombus. So one less thing to worry about. Couple of notes here about a kite, everybody, things that we may have forgotten. A kite is a quadrilateral, 4 sides, and it's got 2 pairs of congruent sides, but the unique thing about a kite is that it's the sides that are consecutive or next to each other that are congruent. So AB is congruent to AD in this kite, and then BC is going to be congruent to DC. So that's an important thing to note. The other important thing is that the diagonals in a kite are always going to be perpendicular to each other. That's important. And one last thing worth noting, everybody, is that when it comes to the diagonals right here, one of them bisects the other, but not both. So in this figure right here, if I called this point E right there in the middle, BE is going to be congruent to ED right there, but AE and EC are not going to be congruent. So that's some important information to know about a kite before we get started. Okay, let's take a look at this example here and see what we can do to come up with the area of this figure. So step 1 is always the same. We're going to start with a formula here that the area of a kite is going to be 1/2 times diagonal 1. There you go, multiplied by diagonal 2. So let's fill in what we know on step 2, but here's where we get a little sad here, guys, because the length of one diagonal, well, let's take a look. One of them, I'll do this in red, let's say, is the diagonal that goes from this vertex on the left to this vertex on the right. We do not know the length of that diagonal right there. The second diagonal, the vertical one, is the one that goes from this point all the way up here on the top to all the way down here on the bottom. And we do not know the length of that piece either, although we do have a 12 right here that's part of that, but certainly not all of it. So we've got our work cut out for us here in order to figure out the lengths of these diagonals. But the one important thing that we're going to need to know is that the diagonals are perpendicular to each other. And so, as we take a look right here, we have ourselves a right triangle that goes here and here and here. And within that right triangle, we know the lengths of 2 of the 3 sides. So let's jump off to the side right here and maybe redo this a little bit. We had a leg of 12, we had an unknown leg here, and a hypotenuse of 15. So we had a 12 and a 15, and I'll just call this an X for right now. And the important thing is that those 2 sides are perpendicular to each other. So again, trying to get some practice right here with what we're doing with Pythagorean triples. Let's keep that green. The common factor we can divide out from 12 and 15 is a 3. And then when we divide that 3 out, let's see what we're left with. 12 divided by 3 is a 4, 15 divided by 3 is 5, and we've got a 3 here then, because this is a 3, 4, 5, the most basic of all the Pythagorean triples. Now we multiply out here. The 3 times that 3 is going to tell us that X is going to have a length of 9. If you know your Pythagorean triples, it's much faster than actually doing the Pythagorean theorem. Okay, so back to this problem right here. We now know that this piece has a length of 9. That is not the length of the entire diagonal, though. The entire diagonal from left to right incorporates that 9, but also another 9 located right over here. So the length of one of those diagonals right there is going to be 18. Okay, had to do some work for that one. Now, still more work to be done to find the length of the other, longer diagonal. And that one starts all the way up here on the top and goes all the way down to the bottom and ends at this point over here. And we knew we had the 12. The other piece we're missing is this one right over here, which I'm just going to call y real quick. But I'm not even making you work for this one, guys, if you know your Pythagorean triples. Let's take a look at this right triangle down here on the bottom. Leg of 9. Hypotenuse of 41 tells us that y has to be 40 because 9, 40, 41 is the last of the 5 Pythagorean triples that we asked you guys to know from back in chapter 8. So as we look now at the length of the overall vertical diagonal, we've got a 12 right here on the top and a 40 down here on bottom that we're going to put together to get a total of 52 for the length of that vertical diagonal. And now we know everything that we needed for this problem. So let's grab our calculators and put all this together. The 1/2 times the 18 is going to be a 9, and the 52 is going to get multiplied by 9. I don't have my calculator handy, so that's an 18, carry the 1, 468 square units is the area of that kite. All right, everybody, that's a wrap on 10-2. What did my kids tell me to say? Please like, subscribe, and leave a comment below. Hit that notification button, and yeah, all that fun stuff. I don't know what any of that means, but thanks.